As I said a few times already, climate sensitivity that typically we have been looking at doesn't include biogeochemical carbon cycle feedbacks. So let's look at a schematic of the potential feedbacks that exist in the system that we already know very well, even though we may not know the quantity of the amplification or the time scales necessarily. So the low latitude warming and high latitude warming can have different effects, but we will soon see that in fact when you try to warm the planet even with orbital forcing or greenhouse gases, high latitude, especially the Arctic, tends to warm faster. Okay, so we'll look at some feedbacks there that are unique as well. And you have a global coupling because as you change the equator to pole temperature gradient, the amount of energy you have to move changes, so the whole climate system changes, ocean circulation changes, and then you have all these internal feedback. So the latitudinal moisture transport itself would be different depending on how much warming happened where. And obviously that means clouds will be affected, which have an impact on radiation, which has an impact on albedo, and that is related to ice as well. And increased net radiation with more summer clouds can be a negative feedback here, but it can have impacts on atmospheric heating, which affects high latitude warming. So you can go from there to there, and you have vegetation feedbacks and snow melt. So albedo feedbacks are still very strong, but you have shrub growth, what else do? Cloud feedback. So unfortunately this only showing the one feedback, but when you say terrestrial coupling, obviously it includes dynamic vegetation, desertification, mountain snow melting, and whenever you change vegetation you are going to change carbon cycle as well. And in the marine coupling you are also going to change photosynthesis, primary production, upwelling, and of course carbon cycle. So carbon cycle is implied in this, but I also want to point out how complicated things are in reality, right? In a model, I just want to emphasize, in a model you don't have to put all these in explicitly. If you have properly represented atmosphere, hydrosphere, cryosphere, biosphere, and so on, these are solutions that emerge on their own. So you'll have to deconvolve them by looking at model simulations, model outputs. You have to do lots of analysis to understand how the model is producing the response to any particular perturbation or in the mean climate. The climate sensitivity that we looked at briefly before, we'll look again. It can be considered as the initial blackbody radiative response, delta T0 estimated, let's say, as 1 Kelvin for a forcing from a doubling of CO2, which is estimated at 3.7 watts per meter squared. So that is the climate sensitivity, which is modulated by feedbacks. So this is why I'm showing these feedback loops and implying that these are not the only feedbacks, even though those are the most often considered. And ice albedo feedback is obviously dominant, but at what time scale? At anthropogenic time scales or decadal to century time scales, is ice albedo feedback as important as, let's say, vegetation feedback? We have to figure that out, right? Looking again at the climate responses at global scale for paleoclimate, the sensitivity is defined as a feedback factor F times delta T0. So here we said if we had no feedback, 3.7 watts per meter squared radiative perturbation coming with doubling of CO2 would change delta T0 by 1K. But then it's never that simple because we have all these feedbacks, right? So obviously feedback is written as 1 over 1 minus G, where G is a gain factor, like in electrical engineering, where you ramp up the voltage or the current, right? So this is the same, and obviously if G is less than 1, you have a positive number here, and if G is greater than 1, you're going to have a negative number, and if G gets close to 1, you're going to have amplification by a lot, right? But G is not just one feedback, you have multiple feedbacks, so it's written as a sum of all those feedbacks we saw before. Okay, this is in a very simple way, and we have seen this before in another form, but essentially this shows that the sensitivities are not constant, which means that the feedbacks we will look at from the past are not all relevant for global warming. So we will have to find analogs which provide us some insights into what feedbacks could be most critical for global warming as we keep perturbing with fossil fuel burning. So for the instrumental period, these are the most likely, so likely, and then so this is very likely and this is likely. So you can see some of them have a long tail. So in the instrumental period, which means since Industrial Revolution, let's say, or 1850 or so, the tail is very long, but more and more model simulations and data analysis tell us that these high numbers are very unlikely. Okay, so the current mean climate is somewhere here. General circulation models are somewhat within the range, but not quite. Last millennium, volcanic eruptions, we will look at a little bit more, as I said. Last glacial data, last glacial models. You can see models have a larger range. Proxy data from millions of years ago. Expert elicitation, so these are people estimating based on data and their interpretation of the perturbation and the responses to estimate climate sensitivity. And this is combining different lines of evidence, so somewhere here. These are difficult issues, but still we need these, so we have to deal with them as they come. Let me stop there and come back to polar amplification in the next podcast. But the main message is that climate sensitivity is very much dependent on feedbacks, and those feedbacks have carbon cycle feedback as an important factor. And we will look at that a little bit more. We looked at the carbon cycle before. We'll try to look at the potential feedbacks, not only in this chapter, but throughout the course. Okay?